electrical code, that's kind of my game these days. And I'm on most of the standards committees related to PV systems, both in the United States and internationally, as well as chair basically all the committees related to the National Electrical Code at NFPA. And so it's a somewhat enviable position to be in, but don't envy me too much because it comes with a lot of pain and suffering. So, but I will try to answer as many questions as I possibly can about the code. We're making huge changes in the 2017 code, lots of things going on. We're at a position now where we have the credibility where we can do that, which is this was the first code cycle we could really go far and do things that we wanted to do, which is going to be good for the future of PV. But today we're not going to focus on the 2017 code. We'll probably save that more for tomorrow because it is getting into its advanced things. Well, we may refer to it a little bit here and there. There's a lot of simplification that's going on in the 2017 code, things like that, which will be helpful. But for most of you, those types of things are going to be down the road, and particularly, how many folks work in California? Yeah, a huge number of folks, and California is 3 years behind the code cycles, so you're not going to see the 2017 code until 2020. We do get benefits out of the newer versions of the code in California, but they don't always translate the way we'd like it to. So we want to make today as useful as possible and address things that you're specifically needing to get help with, maybe your sticking points with local jurisdictions, needing some background on, things like that. Hopefully I can give you some understanding of background. And before I start any class, I like to ask the crowd what things would you like to have covered today, and we'll do our best to cover those things in some type of an order that'll make some sense. So anybody want to start us off, and we'll spend about 5 minutes talking about things that we want to talk about today. If it is an advanced topic, we might get to it today. I can't guarantee it, but if we don't get to it today, we'll definitely get to it tomorrow. So, who will be first?
How to calculate the maximum allowable PV system based on different codes, code years.
Calculating maximum allowable PV system. What do you mean, on a roof? You mean for the service, or for what specifically? I mean, I can put in as big a PV system as the utility as my land will fit.
Bill, I think I heard something you didn't hear what you said about breaker sizing based on.
Okay, so talking about the service side, okay, that's helpful. I mean, I can put in a 400 amp service too, and I can put in a ginormous PV system. So if we say we're stuck with what we got, we're not going to do a service upgrade, stuff like that, based on existing system, existing service. All right, that's a good one. Another gentleman here. Best practices of what?
Anytime you come across a subject goal, it might be the best practice, the best way to utilize it.
Okay, my opinion of how to do it best? Okay. Well, if we get on a little tangent, then ask that question in the middle of it. How about that?
Along those lines, remember last time you showed about fires were caused by not deburring the conduit, things. So along the best practices, maybe the key things that are most important for safety, because you have the code, and then you have what really could go wrong.
Sure. So what really matters, maybe. Yeah, I think that's certainly been one of my approaches, is that there's a lot of stuff in the code. Most of it we don't use, but what's the stuff that really matters? And in 690, we had a ton of stuff that we never use. And so Article 690 is about 15 pages in the code right now. And hopefully we've gotten rid of about 2.5 pages of that, maybe 3. Unfortunately, rapid shutdown added about a half a page back. But
this, you may want to dismiss this, but last year you mentioned that you're pushing for 2017 code to change the bus bar roll from 120% to 140%. Is that going anywhere?
Not yet. So yeah, the 120% rule, what we did do, which was kind of a last-ditch stand, and it did go through, is we put it in specifically that 1 and 2 family dwellings, you do not have to be at the opposite end of the bus bar. So center-fed panels, disallowing center-fed panels is a thing of the past. We got to write articles to, there's several jurisdictions that we're waiting on that. The voting will go through, actually we voted on the ballots this past Friday. We'll know by the end of this month. That one's pretty assured, guaranteed to go in. And then we can start releasing that this is a past thing. And so we're done with it. And 1 and 2 family dwellings don't have to worry about center-fed panels anymore.
Somewhat related to the capacity issue is there any push by anybody to get counties or cities to allow line-side taps? I know they're okay in the code, but some counties still say no.
So push for AHJs to approve supply-side connections. It's a really good question. I mean, and I guess maybe it's because we're presenting it the wrong way that people are against it. It's if you're allowed to run a set of service conductors off a service drop, why wouldn't you be allowed to run a parallel generator connection? And nobody has a good answer to that. It makes no sense. There's another question back here.
A specific answer for one problem I have is like in the junction box. So I'm coming in with my PD wire and then going out to my inverter. So using wire nuts. And then on the ground, I've had some inspectors that say that has to be an irreversible crimp. Our argument was that's an equipment ground, not a grounding electrode. Is there a specific connector that you're supposed to use? We had one where he said it had to be like a DC certified connector, which we could never.
Oh, yeah, there's no such thing as a DC certified connector. That's baloney. Connectors are based on voltage and wire type and things like that. So if anybody tries to tell you that, they're smoking something. Yeah. So it's all about the proper termination in the proper location with the proper materials. Whether it's copper or whatever. But as far as your other question was about an EGC termination. EGC terminations are clear. Where we run into problems is that because the code has this mess in the grounding section in 690 about additional array electrodes in 690-47D, that you get this confusion that what's coming off the roof is actually an electrode conductor rather than an equipment grounding conductor. 2017 code is excruciatingly clear that it is not a grounding electrode conductor, it's an equipment grounding conductor. And it always has been, and technically always should have been, but it's because of bad code language that we have what we have. And that's frustrating to me personally because I spent, I got it out of luck, got it out of the 2011 code, but then the International Association of Electrical Inspectors, who I am a member of, got it back in. against.
The microinverters,
Yeah.
then that's a grounding electrode.
Well,
String inverter, then that's an equipment ground.
that's not the way it's differentiated in the code. Some inspectors may read it that way, but most of your microinverters today are ungrounded. So a lot of inspectors have, and especially here in California, no longer require a grounding electrode conductor run from the roof for the DC side of the circuit. But they may require it because of 69047D, and we'll talk about that a little bit. And that's the difference between irreversible splice and a reversible splice. But quite frankly, there are irreversible crimps on the market that you can get that are for the right size wire you need. And so if you do run into a situation like that, just use an irreversible crimp and just don't get into a large discussion with the guy or the person, whoever it might be. It's unfortunate, and unfortunately it's bad for them too, because the code's unclear. You know, that's the problem with anything in the code, is that if it's unclear, it's not just bad for the installer, it's bad for the enforcer. Because lack of clarity takes you to conservatism as an enforcer, right? See, if you're on the contractor side of the equation, lack of clarity goes, well, I could read this both ways. I'm going to take the easy way out here. If you're the enforcer, you go, I could read it both ways, but what if it's the wrong way? I'm going to take, so you're creating that craziness, which is why the code has to get clearer and better. So.
I was just going to amplify on that for you to cover grounding and bonding pretty heavily, because that seems to be the main area that there's a lot of applicable with inspectors.
Yeah, grounding and bonding. Well, why is grounding and bonding a big deal? It's because most inspectors that have any electrical knowledge, whether they know anything about PV or not, know something about grounding and bonding. Maybe enough to be dangerous, but you inspect what you know. And so, and we see this all the time. An inspector read an article somewhere. Here's a crazy one. We have a PV on one end of a wire, and we got a circuit breaker on the other end of that wire, and we've got to upsize that wire for 120% of the sum of the output of the PV system and the breaker. And it's like, who gave them that idea? Well, there was an article written in the IAI magazine, written by John Wiles, and he said that. Completely wrong. But you got inspectors that are going to come out and say, oh, well, you're going to have to upsize this wire here. Absolutely ridiculous. I'm actually writing a letter to a jurisdiction here in Southern California that's writing up my design on that very issue, and I'm having to explain to them that they got bad information from a bad article, and it was wrong. What's that? Yeah, somewhat. But unfortunately, you get one piece of information, and that's the correction, right? So I read an article, and the article said I have to do this, and so now I have to correct. So every installation, I correct this, because I have no idea what the rest of it is. Even though there could be bad wire management, there could be all kinds of things that are bad with the system, no signs. I read an article that said you shouldn't ever do this. You shouldn't ever put a circuit breaker in a center-fed panel. Can't do that. Because, oh, guess what? Where did they get that from? They got it from an article written by the same person, equally uninformed. And it's like, are you kidding me? This is not a problem. And so now we've, in the state of California, we've reinstalled perfectly good panels. And this is one of the reasons why I was so upset about it. These center-fed panels are no older than about 20 years old, because that's as long as they've been on the market. They really haven't been on the market that long. No, not a split bus. It's a center-fed panel where the main breaker is in the middle of the bus. Okay? A split bus is not an issue at all. Okay? But this is where the bus is continuous in both directions. That's right. You either have two opposite ends or you got no opposite end. And so basically his article said you don't have no opposite end, and so you really can't do 120%. The only thing you could do is downsize the main breaker. And in every case I've ever seen, even though people do it in the field, I don't know that there's any legal way that you can downsize the main breaker in most of these panels. they're not designed for that.
Remove the break. So there's an Eaton panel you could still buy today that's one space off the main. That's center fed. I mean, it's one space off the end.
Yeah, exactly. There's one at the far end and one.
It's center fed, so you know what we do? We just move it down a spot.
Yeah. It's just craziness. It's anything that, if it doesn't make sense and it's crazy, we need to stop it. And so that's and this is one of those things. And if we compare it to just the reason it upsets me is that, California, we have millions of old panels that are just rotting off the wall of people's houses that are getting ready to burn their house down, and those things need to be replaced, and yet we're leaving that guy on the wall, and we're ripping out a brand new panel, perfect, in great shape, far better than the panel that's rotting off the wall, because somebody said that it was important and it was a safety issue. No, the safety issue is that old panel, and that thing's getting ready to burn your house down. So anyway, so that's just a little bit of rant on my case there. So we can keep adding to this, but this is helpful in kind of getting us going in chatting about stuff for today. Let's see if I can't see this because I'm doing two different. I should go do it this way then. I'll duplicate it. That's gonna.
So along those lines, I've had to deal with what I would call a lot of jurisdictions overstepping their authority, and in many cases have been successful, but you're dealing with it on a national level. We're dealing with it on a local level. Just your insights and guidance when something's clearly in the code, something's clearly UL listed, and you still have the AHJ saying, "Oh no, we can't do that," or you need an engineered stamp drawing or whatever. Right. Best practices and how to try and escalate it and get what is appropriate resolution.
Yeah, that's a problem in construction. And it's probably a bigger problem with solar construction than it is with other constructions because there's more new and different stuff out there. But California pushes the envelope on all kinds of things in the built environment. So we've got all kinds of new things coming down the road. And other states as well, but the first and foremost thing is trying to establish a good relationship with your AHJ from the very beginning, and not, realizing that first impressions mean everything, and this is just people work. The fact is that if we tick somebody off in our community, and we're going to work in that community for a while. That was a bad thing to do, and that's going to make life hard for a long time. You want to have a receptive AHJ that's willing to learn and actually get them engaged in the learning process and encourage them. And so when I talk to AHJs, my first and foremost concern is to get them interested in the technology and get them interested in this stuff. They have a fairly thankless job in a lot of ways, maybe a boring job in a lot of ways, in a lot of what they're doing, and this is something that's kind of cool. And over the years, I've been pretty successful with that to the point where a lot of the AHJs I've worked with end up with PV systems on their own houses, and I consider that a win. It's like if I can get an AHJ to put one on their house. In fact, how many folks from Hawaii here? Nobody from Hawaii in the room. Okay, whatever. Hawaii's a great place. But Big Island of Hawaii, the big kahuna on the Big Island of Hawaii, he was tough. He was a stickler. And the contractors on Big Island couldn't stand this guy. And he was like, oh, he's so anti-solar. I can't believe he's so anti-solar. I'm like, I really don't think he's anti-solar. He installed his own PV system on his house himself. It's like, it's not anti-solar. You just got to figure out how to work with the guy, and understand where he's coming from, because he doesn't like crappy work, and so if you're giving him crappy work, then he's going to not be your friend, and so you got to figure out how to get along. So, and unfortunately, given the culture on the Big Island of Hawaii, crappy work is pretty normal. That's considered kind of typical of the culture, and so he's fighting that culture as a Hawaiian. I mean, the guy's straight up Hawaiian. He's not like some mainlander around over there to set all those folks straight. So anyway, so yeah, working with people is huge. And you know, we was chatting with somebody right before we started today, and something very clearly in the code, and the inspector didn't want to hear about it. You know, it's written in the code in black and white. And so if you got somebody that won't actually look at what's written there, you got a huge problem on your hands. I mean, there's nothing to solve that, because you know, if you're not willing to read the code, you're saying, well, this is the way I think it should be. I think a lot of things should be different than the way they are right now. You know, I could think of a million things I'd like to see different, but you know, in this case, it's written in the code. This is the way it's supposed to be. You know, and the fact is, there's things in the code that I wish weren't in there, and that's why I work hard to try to remove the things that don't make sense. So I'm just going to show these next couple slides because, being a basic class, you know, I don't like to assume that people understand this stuff, and even people that have been doing it for years. The photovoltaic effect and how it affects the electrical circuits and everything like that, the whole code is built around that. And the more we understand that as a foundational principle, we can understand how to write the code correctly. And so it's a current limited source, which all of us know, but we have to remind ourselves that, you know, we have a short circuit current that is absolutely limited. It's limited by how much sunlight we've got. We have an open circuit voltage that's absolutely limited by the number of cells we put in series and things like that. Our power versus voltage curve, obviously we want to operate this thing on the knee of the curve and all that stuff. And that's how we design our systems, and we have inverters that do that for us. But then we have to understand that our current varies, so this IV curve actually just slides up and down. It doesn't change shape, it actually slides up and down as we get more irradiance. More intensity of light, we double the intensity of light, we double the intensity of the current, and so this is the effect we see. Now we're going to see a little bit of a voltage difference here, but that's just because we're cutting off the IV curve a little bit differently as we go down in irradiance versus up in irradiance. And so all of the things that are in 690.8 about current are related primarily to this curve and how it reacts to sunlight. All right, and so then we go into voltage, and we see that the IV curve slides left to right with temperature. So as the temperature goes up, the curve slides to the left, or to lower voltage, and as it gets colder, it slides to the right. Okay, and this is just the physics of the photovoltaic effect and what's going on in the band gap, in the PV cell, and all that good stuff, which results in what we see in the field of lower voltage on hotter days and higher voltage on colder days. And we can see that, you know, if somebody wants to tell you there's a difference in the short circuit current of, you know, at different temperatures, that's true, but look how close they are together. But if you look at the operating current for all these curves are identical, absolutely 100% identical. So we have operating currents that really do not change with temperature. We'll go back to that previous slide. We have operating voltages that do not change with intensity of light. So your operating voltage stays the same. And those are some foundational concepts that you have to get into your head, and they'll keep you for a long time in understanding why the code's written the way it is, or how it should be written, let's say. You know, that IV curve, we can't underestimate how important it is to understand that, and why it's a really good idea in a lot of applications to get away from it as much as we possibly can, because it has some severe limitations to us. Okay, so you know, a lot of folks say, well, I don't want to add electronics into my PV array because that adds complexity, it lowers reliability, and all those things in their basics are true. The fact is, once you start throwing electronics at anything, as you add components and things like that, you are going to have an impact on reliability, but it doesn't come with no benefit or no upside. And that's what a lot of folks don't understand, is that there is a huge upside because the photovoltaic effect has a huge downside, which is the fact that it moves all over the place with temperature. And that's not a good thing. It moves all over the place with intensity of light. So with the, you know, clouds coming with shading and things like that. And these are things that we've had to deal with and mitigate in different ways with string inverters since day one. It's nothing new. It's been going on forever. And so when we see products like N-phase microinverters or SolarEdge DC converters and things like that, I'm not going to use the word optimizer because it's not true. I mean, it's not necessarily, it's either an optimizer or a pessimizer. It's just, depending on what's going on. So it's a DC converter, but hopefully it's mostly optimizing. But anyway, those tools are essentially minimizing the impact of the photovoltaic effect on the rest of the system. And so when we talk about operating voltages and things like that in a PV system, when we're talking about a SolarEdge system or an N-phase system, that has a one module PV array. Okay, from the definition of voltage in current and what is in the code right now. Okay, so we're not having to add voltages up and things like that in the same way that we are with a string system. So a string system, we have 10 modules in series, 20 modules in series, 10, 12 modules, whatever it is. We've got so many modules in series, we've got to do this calculation. It's an end-to-end calculation, and we have to add the voltage, open circuit voltage, temperature coefficients to all those things and come up with a calculation for lowest expected ambient temperatures and all this stuff that we have to do. Well, all that stuff pretty much goes away, and all you're doing is looking at one module, interfacing with one piece of electronics, and then we have this DC circuit, which the 2017 code is actually gone into and actually defined that we have PV source circuits and we have DC to DC converter source circuits. And there's things that apply to both of those types of circuits, and then we have PV system DC circuits now, which is now a term that covers all DC circuits that would happen in a PV system, which would include PV source circuits as well as DC to DC converter circuits, because there's some things that apply to all of them, and some only apply to ones that are driven by PV specifically. Okay, because when they're driven by PV specifically, we have to worry about all those differences that are in those IV curves that we talked about. Okay. So we got lots of parts of the code that apply. Now, just as a little note here, I have Article 480 here for storage batteries, 2017 code. We take all of Article 480, we stick it into a new article called 706, Article 706, and we take all of the battery section of the PV section, which is in the 70s, 690.71 through 74, and we stick all that in Article 706. That's all gone from Article 690 now. But that's the way it is written currently. So here you see the way it is currently, and you can see that we have the storage battery section. We have systems over 600 volts, or actually it's over 1,000 volts for the 2014 code. These last Part 7, 8, and 9 go away with references now. Those no longer are in Article 690, and we'll see why in just a minute. But what we're paring Article 690 down to just photovoltaic system only. And so a battery system that has historically, for the last 30 years, been considered part of a PV system, we're saying, no, you're confusing things here. You've got a power source called a PV system. You've got a battery that's an energy storage system that you happen to be connecting together. Okay, just because they happen to be connected together in a system, they have to operate together, sure. It doesn't mean that the battery is part of the PV system or that the PV system is part of the battery. They're just working together to provide power to loads in your building. And loads are another category. So we have a power source, we've got an energy storage source, and we've got a load. And loads are really well defined in the code, and that's what most people think about. And what we're doing is working on now is we've been working hard on getting the power sources figured out, because they have not been treated well in the code and haven't been a lot of information in there because it's a load-oriented code. And now we have this new section for energy storage, which has also not been treated well in the code and is just kind of getting its own legs now. So I'm going to talk about a little bit about the code updates that have occurred in the last couple of code cycles because they're relevant to most people in the room. I'm going to save, I've got a slide or two here on the 2017 code. I'm going to save that till tomorrow So if you want to go more in depth on that stuff, that's kind of more of an advanced thing. So 2011 code, the code cycle was kind of an interesting one because we got shifted from one panel to another panel, which meant we had to retrain everybody in the panel on what PV systems were. And it was my rookie year, 2011 code for the code making panel. And so there was a lot of things that we wanted to do in 2011 that we couldn't. We didn't get past. And but what did happen is there's a lot of routing and identification requirements, and these are pretty standard requirements in the code. It's really not new stuff, but people weren't doing it, and so you had multiple inverters, you couldn't tell what wires went to whatever, and so the code got really specific in here and said you had to have specific identification and routing and things like, if you've got conductors in the same gutter, the DC conductors have to be bundled together, the AC conductors have to be bundled separately, things like that, which only make good sense, but, and if you've ever worked on a system that was all jumbled up, you can attest to the fact that it can be a nightmare. One of the biggest changes in the 2011 code was series arc fault detection. And so that being the code that we're on in California, now all of our inverters are going to be required to have arc fault detection on them. There could be a separate device that could do arc fault detection, but those products are very rare, and they're typically designed for large combiner boxes and things like that. So normally you're going to buy an inverter that's got arc fault detection built into it. We've been learning a lot about arc fault detection over the last couple of years, and so we found some issues with it in the original test and the way they do the original test program, and those things are getting fixed. And so our inverters that are out today are great at detecting arcs on home run cables. And quite frankly, the vast majority of our problems actually occur on home run cables, but not all of them. So we have connector problems at the home run connectors. We have connection problems at inverters and things like that, and those will pick those up. What our inverters are not very good at is detecting an arc fault between modules within a string, and because of attenuation in the circuits and things like that. So those things are being dealt with, and the new standards and requirements are fixing those things, and a lot of manufacturers have already worked on their products. But arc fault detection is a huge benefit. A lot of people were upset about it. There are some products that have had some real issues, for sure. So as expected, it hasn't been a cakewalk, but our industry is getting better and will absolutely be better for it. I actually did I do a lot of fire investigations, and did a fire investigation recently, and it was installed, it was permitted in the previous code cycle, and it was installed in this code cycle. But because it was previously permitted in the previous code cycle, it didn't have arc fault detection inverters. And so the contractor used lineman pliers to crimp their connectors for the home run cables on all the connectors, and more than half of the connectors in the entire array were loose. One of those connectors came loose, started on fire. This is on a mall. And so you can just imagine, within 10 minutes, there was 6-foot-high flames on the top of this mall. And so they got the fire out, fortunately, because the fire service was very quick to the scene. I'll have to get the video of this sometime, but the first firefighter goes up there with a fire extinguisher, and it's like spitting in the wind. It had zero effect. And but then they got a hose line up there, and within 30 seconds the fire was out. So these fires do happen. That company that installed the system has since made the policy decision that we don't care what code we're on, we're putting in arc fault detection inverters. And so, and a lot of folks have done that. Even, there's definitely places in the country that may not even be on the 2011 code, but is it smart to not put in an arc fault detection inverter. I got a good deal because somebody's trying to get rid of some inverters that don't have arc fault detection in them. The answer is, I'm not feeling that lucky. So 690.64 got moved to 705.12, which is where we have, that's all related to connection to other sources. 2014 code, lot more changes happened in that code cycle because it was the second code cycle with this panel. We have a requirement that our ground fault protector must detect grounded conductor faults, which was not specifically required in the past. And so that's something where the good news is that the industry has gone almost completely to what we call non-isolated inverters. Some people call them transformerless inverters. So most of the inverters you see out today are non-isolated inverters. They have very high resolution ground fault detection, and it detects ground faults on both positive and negative. So we're in really good shape with those products. The old products, fuse grounded inverters, are dogs, quite frankly, from a ground fault detection point of view, and they have some real issues. Arc fault protection now required in ground mounted systems. That was another big change in 2014 code, not just roof mounted systems. 2017 code does a little more modification on that, but one of the biggest things that was added to the 2014 code was rapid shutdown requirement. That rapid shutdown requirement is fairly short as far as the words, and so there have been, as expected, some enforcement issues with that, but we intentionally tried to keep it short so that we didn't over-specify how to do things, but it does require that conductors leaving a PV array be shut down, and the 2017 code goes quite a bit further than that. 690.15 requires disconnects on combiners, so that was a new requirement. Now the reality is that most combiners out there today do come with at least a disconnect option, but that was a requirement that went in the 2014 code. And 690.13b requires separation of DC and AC conductors in a PV system. So this was a big change. This was what I considered a loss in the 2014 code, where the International Association of Electrical Inspectors felt it was important to actually not just bundle them separately, but actually have them in physically different raceways. So now you can't have a gutter with DC and AC in the same gutter without some type of a partition. Okay, so you would have to have a partition. Partitions are available for gutters, but you'd have to specify the gutter up front that way and all, and you can't just put a piece of paper in there or something like that. So, so that's unfortunate, but it is what it is, and so we have to follow that for 2014 code.
Combiners requiring disconnects, are circuit breakers acceptable as disconnects in combiner blockers?
Sure. Yeah, I mean, that's, yeah, it's got to be a load break switch. So those would be, you could have load break switches on every single circuit, or you could have one master. Either way would be okay. 690.13 through 17 were completely reorganized and rewritten, which is the disconnecting means section. Certainly better, but I would say it's not great, and we spent a lot of time on that. It was, there were some good proposals. It actually paved the way for a complete change of how to do things in the 2017 code. So for that perspective, that was a good thing. Cable tray is talked about, specifically in Article 690, specifically allowing it for PV wire of any size, as long as it's supported every 12 inches and then secured every 4.5 feet. In 31D, it talks about multi-conductor TCER and USA2 being allowed for AC, for utility interactive inverter output circuits. And that had a lot to do with N-phase inverter cables and things like that, and other companies' cables. That's probably going to change, it is changing in the 2017 code where they're basically requiring that these cable systems be listed. So we're not going to be running our own TCER everywhere. It's going to be part of a list of assembly. 35D, which is part of the ungrounded section, 690.35 is ungrounded systems, and 35D is the wiring methods, and it added metallic jacketed cable assemblies and underground cables to the list of options for 690.35 for ungrounded systems. Just as another 2017 reference, we got rid of 690.35 altogether in the 2017 code, completely gone, because all PV systems will be wired identically in the 2017 code. Doesn't matter how you ground it. 705.12d, that was something we tried to do in the 2011 code, was to overhaul it, and we got it overhauled in the 2014 code. It's a lot more detail in that. We'll spend more time on that. We may spend some time today. There's some questions earlier on about the 120% rule and all, and so we can get into some of that. And it does address things like the idiocy of having a PV breaker on one side and a supply breaker on the other side and trying to add 120% to that line, which is absurd. And 705.31 basically states that if your overcurrent protection device on a supply side connection is more than 10 feet from the connection point, then you'd be required to put in current limiter. So it gives you a specific distance on how far you could go before you would have to put in something at the connection point. A current limiter is basically, so when we talk about an overcurrent protective device, or OCPD, it's not the Orange County Police Department, overcurrent protective device in the code, that device does two things. And it might even do three things. Its primary purpose is to protect from overcurrent, okay? And so that means that, we call it overload. So if you're putting too much load on a conductor, then you could damage the conductor, cause a fire hazard. So that's called overload. That means putting too much load on it. Second is it's designed to address faults, okay? So if you get a fault on your load or on your conductor, then what's going to happen is you're going to get a huge inrush of current, and that device has to operate very quickly in that case and safely, and not explode and things like that, because we have this big power source called the utility behind it. And so our breakers have to be rated for the short circuit duty of the utility and all this kind of stuff. And so they do overload and they do faults. And then, as was mentioned earlier, a circuit breaker could also be a disconnecting means. Okay, so that's an overcurrent protective device that also has the function of disconnect, and that's called a circuit breaker. Okay, so when we're connecting to the line side of a service disconnect, we are connecting essentially directly to the service conductors of the utility company, and there's nothing in between us and the utility other than a big old fuse on the other side of that transformer that will allow far more power through that wire than that wire could ever handle, and it will fuse the wire and blow it off the wall. So the question is, how far would you be allowed to go before you have to put in a device that would protect against faults? And so what this says is 10 feet. And if you got to go more than 10 feet, then you got to put this special device called a current limiter, which it doesn't do overcurrent or overload protection, it only does fault protection. So a current limiter is a fault protection device, not an overload device. So let's say you're running a 200 amp circuit to the supply side of a service, all right, and you got to go 15 feet or 20 feet, whatever it is. You got your overcurrent device there. Then at your connection point to the main service conductors, you're going to have a current limiter on there. That current limiter is not going to trip at 300 amps. You got a 200 amp circuit, it's not going to trip at 300 amps. It's not going to trip at 400 amps. It's not even going to trip at 1,000 amps. It's going to trip at 4,000 amps, maybe 5,000 amps, because it's protected against fault current, not against overload. So they're set way up because they have one function and one function only. And then 705.100 talks about three-phase systems, and the fact is that utility companies for years have been using 705.100 to prevent you from putting a single-phase inverter on a three-phase system. Okay, well, this building is absolutely served by a three-phase system. Most commercial facilities, except for really small ones, are on three-phase systems. Okay, which means that you would not be allowed to use a single-phase device, including an N-phase inverter, on those facilities because of a poor interpretation of articles of 705.100. So we rewrote the way it was written and made it really clear that single-phase inverters are just fine on three-phase systems. It's not the issue at all. It's an issue of the worry is about voltage imbalance on the system. And so a single-phase inverter can either create more imbalance or less imbalance. But that's exactly like a single-phase load on a three-phase system. A single-phase load on a three-phase system can either create more imbalance or less imbalance. And it all depends on where you put it. So utility companies should not be interjecting themselves into the process of what's going on because it's an electrical issue. It's an electrical service issue. And the fact is that most facilities are unbalanced. You know, in fact, I didn't even know this, but it's true, and it has to do with our culture, is that the A phase of almost every service in the United States is the most heavily loaded phase. Why is that? It's because A sounds better than B and sounds better than C. And we have some bad feelings about our childhood of getting a bad grade. And we put, you know, if we've got a choice, we're going to put it on A. It's exactly what it is. It's something up here. It's subliminal. But A seems to get it, you know. And this is true throughout the United States. And so it's so true that the utility companies change their A phase to their customers. They rotate them going down the street. Okay, so they have A, B, and C phase that they're running down the street, but you're really getting CBA at your facility so that you load up your A phase, but it's really loading up the B phase. So it's just they're playing games with you, but it's just funny that that's true. So this is all about balancing systems, and you may run into that, but occasionally that does come into play. We'll talk about those things more tomorrow. And so that's kind of the things that are going on. You can see a lot more changes in 2017 code. The way the 2014 code is written currently, if we've got multiple inverters in multiple places, we do use placarding at each place that they're connected. So we have a building like this. We could have several sub-panels that have different PV systems connected to them. We're not required to bring them all to one location. But at each location where we have connections made, we have to have placarding, and it has to essentially show where the other locations are. So we don't want to go crazy with putting 2 inverters on every sub-panel in a building when you got 20 sub-panels. But if they are in different places, then they would have to be placarded as such.
Can you back up this one? In the example, entry is required from
Okay, so there's an exception. The exception says that if everybody's grouped in one place, don't have to put any placarding on there. And it's just in case somebody said, oh, you got 4 inverters here, you got to put a placard on each one of these inverters. Well, no, they're right there. It's like, what do you mean? Like, if they're in another room or another building, for sure, you know, or another place, but not if they're all sitting together.
Well, that's the way I understood it. I ran into an inspection service a couple of weeks ago where multiple inverters, but what they wanted was all disconnects to be grouped.
Yes. No.
I'm like, where did this come from? It goes from the NEC.
No. Yeah, and when somebody quotes the Bible like that, you go chapter and verse, buddy. Come on, work with me in a nice way. And this is how you do it. It's like, it says that in the code? Well, could you please show me where that is? I mean, I'm learning. I make mistakes, and so could you help me understand this? If they blow you off and say, well, no, it's in there, just don't. No, that's bullshit. I'm sorry. No. Chapter and verse. We got to go to chapter and verse. And that's why you have to know the code too in Article 690, because most inspectors are not really well versed with 690. They may know chapter and verse somewhere else, and they'll quote that and show it to you. So you have to say, oh, but you're right about that, absolutely. And for a normal system, absolutely, you got to do that. But in 690.13F, it says this. And then you go, oh, wow, I never saw that before. I guess you're okay. Off you go. So it's, you really do have to know it.
We had that, you probably know the article better than me, about service disconnects.
Right.
And what I found happening is they were considering that PV was a service.
Right.
And then I had to say, no, it's not a service. It's not an independent power source. But then they gave you the placarding. Well, it's not operational without the grid power.
Well, it's called interconnected. A parallel generator is the term in 230. I'm sorry.
But they were quoting it under 200 as a service.
Right.
Which is why they were saying group the disconnects. In our case, and we were able to work with them and get that changed and then use the placarding that says, no, the PV disconnect is located X and the service disconnect is located Y.
And there's other examples like fire pumps and things like that where they're not even allowed to be in the same location, so that they're not operated at the same time to prevent people from de-energizing stuff that's safety required. So those are things, and it's very important to understand that, just to kind of riff on that for a minute, is that a PV connection is not a service. Even though a lot of the language for services have been pulled into 690, just because it's written like that doesn't mean that it is a service. And so it doesn't count in the six-handle rule for services. And so if you look at the list in Article 230, it says, here are the things that can be upstream of the service disconnecting means. The service disconnecting means can be up to 6 handles in the same enclosure and different enclosures grouped together. And so if we're upstream of that, we're a 7th or an 8th or a 10th. There is no limitation on how many times we can connect a parallel generator upstream of the main service disconnecting means. And it's not a service, but the problem comes when it's all about counting. And counting says that as long as I have less than 6 disconnects in my view, I'm good and I'm happy. If I count 6 disconnects on a wall or less, if I have 3 disconnects, I'm really happy. If there's 4 or 5, I'm getting nervous. If there's 6, then I've got to worry. And if there's 7, my life comes apart, right? And it's like, well, wait a minute. Why are you counting all these things? They're not even necessarily service disconnecting means. One might be to a well pump. One might be to something else. And why are you counting that in your six-handle rule? So it's interesting. There was a question over here.
Yeah, this just came up in a county by us, and there was a disagreement among the county, and they had to come up with a decision about, for a line side tap, what my electrician calls a service disconnect, we put in, and there was a question whether it should be bonded or not.
To the case, or to what? So yeah, the easiest way and the simplest way that I can explain a parallel generator connection versus a service is that it looks like a service, it quacks like a service, it's wired like a service, it's just not counted. Because a service serves loads. Okay? So there's no reason to wire it any differently than you would wire a service disconnecting means. For instance, bonding the case of the service disconnecting means. Because the reason you bond it is because if there's a fault in that unit, that's the only thing you got to clear the fault. So I don't see that issue's any different whether you have a parallel generator or not. It's the same issue.
They came back and said we had to unbond it.
Had to unbond.
We had to unbond it. I mean, it was bonded, and our inspector thought that was right, but he says they're having a big conversation and they're going to make a ruling in a week, and they came back and said you have to change it.
It's a fault issue, so in my mind we wired exactly like a service, and there's another reason why we wire exactly like a service, because if at any time in the future we decide to turn it into a service, then it better be wired exactly like a service. Okay, so because what's going to happen? We've got a 200 amp PV system that we wired upstream of the main. Well, we decide that we've got this massive feeder out there, and the code allows us to put a 200 amp PV system on the other end of the feeder now in the 2014 code. So no longer do we have to make a single connection at that point. We can make the connection at that point out there, and now we can put in a load panel, a 200 amp load panel on the end of this without having to run a whole nother separate feed out to that location. We can take advantage of the wire that's already been run, but it now counts as one of the 6 service disconnecting means, okay? So we better have at least, a little room there too. So we wouldn't, if we're already done the 6 service disconnects and we're doing a 7th, then that's got to stay a parallel generator connection, has no option. That's where you're stuck. So, does that make sense? So, but bonded versus unbonded, I think it's safer to have it bonded. But it's ultimately bonded through everything anyway. It'll get there. Okay, so that's a little bit about multiple. The 2011 code added this stuff about maximum system voltage and using AHJ data rather than all-time lows for that. And that was really to address the fact that especially in colder climates, which some in the room deal with, we're getting people having much too conservative voltage calculations on your PV systems, which is causing PV systems not to operate well in the summertime. So in fact, I was talking to somebody at lunch, and area like the Midwest where they have very cold winters, very hot summers. And that's, again, you're stuck with this PV changing with temperature, the voltage changing with temperature, and it can be a real challenge to design a PV system to operate within the bounds of hot to cold. And so what we want to do is be able to not use an overly conservative temperature. And that's what this AHJ data is all about. And there's the website where you can go to get the AHJ data. Of course, there's the temperature correction factor table. Now it says up to the 2014 code, it says that this table shall be used only when, essentially the way it's written, that if you've got the correction factor coefficients, you have to use the coefficients. That this is only used when you don't have the coefficients. Well, quite frankly, it's a very conservative table, and it's a very easy table to use. And so there's really no reason to require a calculation. If you use this table, you are going to be more conservative than the actual need. And there's nothing wrong in the code with having things more conservative. Code's very conservative about a lot of things as a basic calculation. So in the 2017 code, this is added back in as you can apply it to any crystalline silicon system, and if the calculation works for you, there's no problem with using it. And so there's the calculation for, by the way, these slides are going to be available after the show to download and stuff like that, so don't worry about taking too many notes here. But this is a calculation using the table, a similar calculation using the coefficient. You can see that it's a lot lower voltage, but not necessarily low enough to actually put another module in series. But where we do run into problems, going back to that one, is where we're at 605 with a very conservative calculation, but we're under with the right calculation or a less conservative calculation. And we always want to put as many modules in series, especially in larger systems, as we possibly can. Because essentially the home run wires, there's a lot of benefits to doing that. So let's just say we have a system that's got 1,000 source circuits in it, big system. And by putting one more module in series, we get rid of 80 source circuits. That's a big deal, right? Okay, so that's a bottom line savings right there. You've got bottom line savings for the fact that you're running less wire, you've got less conduit, you've got lower voltage drops because you're running at higher voltages. All these things come into play, so we always want to push our voltages as high as we possibly can. That being said, on smaller systems, pushing the voltage as high as we can is not always an option, which is why string inverters are actually a big challenge in a lot of residential applications, because we're actually having to, most of the string inverters that are out nowadays have a very wide DC voltage input. So now you've got 150 to 600 volt DC input, and that way you can have short strings and long strings on the same inverter. And most of our inverters have dual inputs, so you could have one input having shorter strings on it and one input having longer strings on it, which is nice, and things like that. So those are trying to give some variety, and that's because the string inverter has always been a very difficult inverter to build arrays for on residential applications. Always has been, always will be. So the more we have a wider voltage limit, the more DC inputs we have. Well, where is this going, right? Think about it for a second. That string inverter is trying to accommodate the problems with the string inverter, which is that it's got a very narrow voltage range. The old school ones did. So now we open up the voltage range, gives us more options. And then we have the problem, well, I can't fit that many modules on this face of the roof, so I've got to put less modules on that system. So now I'd like to have two different voltages. Well, if I got two different voltages, what if every module worked on its own? That's the only place we got to go with this thing. So we're talking about trying to, especially in residential, we're trying to put as many modules on a roof as possible. Okay, so we have setbacks required for the fire service now. Okay, and that's getting changed, by the way, for the better. We're actually reducing the ridge setback from 36 inches to 18 inches in the 2018 fire code and NFPA 1, provided that the array is less than a third of the overall roof area of the roof. So that's a big benefit. We're also getting rid of, essentially getting rid of one of the side 3-foot requirements and things like that. So there's a lot of changes going on on the roof access issues with residential. But ultimately, at the end of the day, we want to draw on a roof where you're allowed to put PV modules, and that's respective of vents, combustion appliance vents, chimneys, valleys, hips, all the things that happen in a roof. We want to basically draw on a roof the allowable places you're allowed to put PV modules, north and south face, right? Think about it, folks. On a low-pitched roof, the north face of a building produces a ton of energy. This is not well known. You got to run the calculations. But the fact is that if you have a due south-facing roof on an 18-degree pitch, 4 and 12 pitch, which is common here in California, the 18-degree pitch on the north face of the roof produces almost 80% of what the south face produces. Well, with the price of modules, why are we so purist about it's got to be on the south face of the roof? No, if I want more power, I stick them on the north face of the roof, okay? Which means I have to have a power conversion system that can deal with those kind of crazinesses and things like that. And so anyway, so that's where things are going, and but that's just an aside. So that's, but as far as, once we decide how much area we have on the roof, then we want to just stick as many rectangles in that area as we possibly can. So it's all about fitting as many rectangles as you can fit on the roof. And then having an electronics package that can address any number of modules that I got to set on the roof. And then we get back to the question you asked earlier, what's the maximum I'm allowed to put on this house? And so now your question is, what's the available roof area to even put panels to start with, meeting all the code requirements, and then what is the maximum my service will allow? And hopefully my service isn't the limiting factor. It often is the limiting factor, and then we have to look at supply side connections and stuff like that. All right, so that's what this stuff is all about here. And this is just a voltage coefficient in volts per degree C, whereas this is percent per degree C, and it's just two different calculations. They'll be close, but they often won't be the same number. Another thing that changed in the 2014 code is to make it specific that systems up to 1,000 volts are actually covered in 690. The way it was written before is anything over 600 volts had to go into Article 490. Okay, so the code actually in the 2014 code had a pretty major revision where a lot of 1,000 volt applications got put into the low voltage category. Because the way it was set up is that low voltage was 600 volts and below, and then medium voltage started at 600 volts and went up to whatever, tens of thousands of volts. And so you have all these requirements that are based on medium voltage that are being applied to an 800 volt system. Well, particularly for PV, that was a problem, and so this basically changed it to say that 1,000 volts or less, essentially, if it's not a 1 or 2 family dwelling. So it kept 600 volts or less for 1 and 2 family dwellings. And why did we do that? Well, the short answer is that we did not want to wake a sleeping giant. And that is we have to work with the union electricians of the United States and their electrician training programs and things like that. And you start bringing up the fact that we're actually allowed to do 600 volts to ground on a residence. A lot of them don't even know that. I mean, because most of our AC electrical systems are less than 150 volts to ground. 240 split phase is 120 volts to ground. You know, and somehow, when nobody was watching, we got 600 volts to ground. Okay? And so if you start playing around and saying, I want 1,000 volts to ground, then we go, well, what the heck? Why are we letting these guys go 600 volts to ground? We should be limiting it to 120 volts to ground. And so we don't want to go there. That's why we left it alone. There are politics involved in electricity. Anyway, so that's non-1 and 2 family dwellings. Overcurrent protection and actually not circuit sizing. The 2011 code had circuit sizing and overcurrent protection paired up, and it was kind of confusing. And so 2014 code, we separated things out. So now that circuit sizing is in 8 and overcurrent protection is in 9, but depending on which version of the code you are, they're either together or they're separate. So this talks about how much you have to oversize your conductors and things like that based upon the current that you calculated in 690.8a. So 690.8a determines what is maximum circuit current. So maximum circuit current for a source circuit, a PV source circuit, is the rated short circuit current of the modules in that string times 125%. Well, that's a very conservative number, by the way. All right? And that's considered the current, and then we have to design our wire to be able to handle that as a continuous current. So we have to actually add another 125% on top of that. That's what this particular B2A says. Now, however, if we're going to use what are called the conditions of use, temperature and conduit fill, then we can use 100% of what we calculated in 690.8a, which is still 125% of the short circuit current. Okay, so we are oversizing our wire, but in the past, copper was cheap compared to modules. It really was. And so, you know, as purists in the PV industry, how many people have been doing grid-connected PV for more than 10 years? A couple people in the room. Okay, back in the day, you know, we never talked about how big the wire was. We always said, you know, if you're worried about it, always round up. Always round up. You know, you think you don't have enough wire, just put some more wire on it. Because it never really made a big difference in the cost. Well, now it actually makes a big difference in the cost. And so we actually pay attention pretty closely to those things. And so we're doing the calculations a lot more than maybe we would have before, and a lot more careful about it. So the 2017 code now adds options on how to calculate the maximum circuit current in a PV system. And it's conservative. It basically only allows these things to be used on larger systems, 100 kilowatts and up. But on a larger PV system, there can be significant wire savings by calculating the current for what it actually is rather than short circuit current times 125%. In fact, we can do simulations on what the current is on a roof-mounted PV system and get very, very accurate numbers on what the actual current is. We will never see short circuit current in a PV system with the ground fault protectors that we have today, because anytime we have a short circuit of the array, ground fault protector is going to trip. And so we don't have to be as conservative as we used to be. And so, but this is the way it's written right now. And on smaller systems, it really doesn't have much of an effect. You know, the easy thing to remember about residential is if you want to know what size the source circuit conductors have to be, number 10. That sounds like a good number. Use that one. You know, and if you're combining circuits together, up to 4 circuits, anything up to 4 circuits, number 6 works every single time in the hottest climates in the United States. So if you want to know what to do, if you're wondering, if you don't want to do the calculations, number 10 for source circuits, number 6 for output circuits, and you're good to go. We actually wrote that into the simplified permitting document for the state of California. And so if you want to go through the simplified process, and if you're not familiar with that, you should become familiar with it. The Center for Sustainable Energy, which is here in San Diego, they have it on their website. But it's a simple permitting process. It allows you to be considered in the expedited permitting that's required by the state of California. But you have to meet all the requirements within that. And so basically, one of the requirements in the forms you fill out is that all your source circuits are number 10 and all your output circuits are number 6. No calculations. Because as soon as you do a calculation, you slow the whole process down. Somebody's got to look at it. Oh, but I could do a number 8. Great. Get in line with everybody else. If you want to get to the front of the line, use number 6.
You have to be a little more careful when you're working with microinverters because the voltage rise.
Correct. Right. We're talking about DC side. So PV source and PV output circuits are the DC side of the circuit. On the AC side, so it used to be good design was no more than 2% voltage drop on the DC side and no more than 1% voltage drop. Some people said 1.5. I was the guy that said 1%. 1% voltage drop on the AC side. Those are still good numbers. 2% on the DC, 1% on the AC. However, calculations on bigger systems, we're going to tend to push those things to more like 3% on the DC side and maybe up to 2% on the AC side. As you go above 1%, you have to start thinking about and actually testing what the AC voltage of the facility is. Because as you point out, you're pushing voltage, okay? And this is not true of just Enphase, this is true of everybody. Everybody's pushing power, and when you're pushing power, there's a voltage drop between you and the service entrance conductors, which means that the voltage at the terminals of your inverter are always higher than the voltage at the terminals of your service equipment. If your service equipment goes up in voltage, you go up that much higher. And so if you're at the trip limit of an inverter, which some of them are very conservative, then you can trip your inverters offline. And so it's good practice to make a habit of every time you go to a site to test the line voltage. In a residence, test the 240 volt line voltage. If it's above 250, take note, because you may have a site where you've got high voltage. If it's above 260, your inverters are not going to even run. So, you've got a huge problem on your hands, and that's very rare, but it does happen.
So I just had one like that. It was an older system with an SMA, and in San Diego here, it was over 130.
Right. So
Under
260.
a leg, and it was getting a fault. And then the fix for it was to they can combine. They had me reconfigure it, the jumpers, so that it only measures leg to leg as opposed to leg, because one leg was high and one was low.
Oh, because neutral was out of whack.
Well, one leg was high and one was normal, coming from the utility.
Oh, from the utility. So it's on their power pole.
And so they could be reconfigured where it's only measuring line to line.
Oh, in the SMA inverter.
In the SMA inverters by changing a jumper, but at the same time the utility's working on it, but at least it won't trigger.
Right.
But that's
for the delta range.
But that's how they measure the that's how it gets that error.
Right. So, yeah, but that has to be called to the attention of the utility because that's a big difference. And that's outside the bounds of what they're required to provide, so. Okay. So for ungrounded systems, the way it's currently written, we have overcurrent protection in plus and minus. So if we have, so in our smaller residential systems with non-isolated inverters, those are considered ungrounded inverters. The array is considered ungrounded. It's actually not true, but we'll go with it. We'll call it ungrounded. One of the good things about having multiple inputs on an inverter is that we can stay away from that third string. So as long as we put 2 strings per input on an inverter, we don't have to have overcurrent protection for most inverters. Most inverters prevent backfeed current. I guess we're supposed to take a break or something, aren't we? Dang it. I think we blew it, right? We blew our break. Just, if you need to take a break, there's stuff out there. Restrooms over there. I may need to take a break later, so we'll see. But anyway, so as long as you can stay, if you go up to 3 circuits or more, you're going to have independent fusing for each circuit. And so the larger string inverters often have products available to do that and are sold with the product or as an option. But if you can at all do it, you want to prevent having to go there because that's double fusing on everything. So if you had 3 or 4 strings going into an inverter, that's a lot of fuses. And whereas if you could have had it broken up between 2 different inputs, that's a lot better. So something to consider. Our larger string inverters for commercial rooftops that go into 30, 50, 60 kilowatt range, you're going to have fuses for sure on those. And they're going to be on the plus and minus because most of those are non-isolated inverters. For grounded systems, the way it's written right now, we only have overcurrent protection in the ungrounded conductor. Now, where things are going in the future, which we have to talk about, is to wire all PV systems the same. What we did win in the 2017 code is we only fuse 1 conductor. All right, ungrounded systems or functionally grounded systems, everybody only has 1 fuse. It is either in the positive, all the positive conductors, or all the negative conductors. You got to pick one. You can't do positive on some and negative on some. They always have to be in the same conductor. So that is the new way of doing it. And what that does is that opens it up for a lot easier to retrofit older systems. Because that's what the biggest problem with retrofitting an older system right now, especially if you've got multiple strings on it, would be that you'd have to install a fuse box that had plus and minus fusing on it. Whereas you might have an existing fuse box that's only got fusing on 1 leg. Okay, so the new way of doing things, everybody uses the same type of cable, everybody uses the same fusing arrangement. And the biggest difference between the 2017 code and the 2014 code is that you're required to have disconnecting means in the positive and the negative conductor. Okay? This is new and this is earth-shaking to some folks, but it is absolutely for your safety and it is so much better. For years, my friend John Wiles, and I've known John for almost 30 years, we wanted to stay similar to everybody else in the country. We didn't want to be weird outsiders, and so we ground 1 leg, and just like AC systems do, and overcurrent protections in the ungrounded leg, and that's the way we do things. And don't ever break that grounded conductor, because if you do, the world's going to come to an end. And it's like, well, here's the problem. you have a ground fault, you blow your ground fault fuse, what happens to the negative side of that negatively grounded system? It goes to 600 volts. And guess what? Every single one of those connections are bolted. So now you're required to work on a hot system or work at night. Those are your two options. Work on a hot system or work at night. Okay, that's stupid. It's been stupid from day one, so we changed that. Said, listen, if you've got a circuit from a PV system, plus and minus have to be broken. That way, if you have a fault in that circuit anywhere, it separates it from the equipment. Don't have to pull out your screwdriver or anything like that. You isolate it from your equipment. Now you can work on the system safely. You can work on your inverter safely. You don't have to worry about bolted connections all the way through your system that are energized at 600 volts in a fault. So
So I have a question on the labeling. So on a isolated ground system, so you used to have the label, or maybe you still do, that says that if there's a ground fault,
yeah,
normally grounded conductors will become ungrounded.
all those went away.
That all went away.
So we got rid of about 5 signs
Okay.
because we're up to like 20 signs in 690.
35 cents each?
Yeah. Or more. So anyway, yeah, there was a lot of signs, and one of the stupidest signs was in 690.35, and it said that essentially that wires can be hot. That's essentially what it says. I mean, if you read it, it's like normally grounded conductors, or, oh, wait a minute, there are no grounded conductors, so these are ungrounded conductors, but they might be hot relative to ground. It's like, wait a minute, guys. If you're touching terminals on electrical systems, you will not last long on this planet. I'm sorry. That's, you're going to get a Darwin Award. You do not need a sign to tell you not to touch terminals. So, and that's exactly what it was. Oh my God. But that was because somebody liked signs. All right, so here's your standard ampere ratings. I always like to, I love this one. There's a standard ampere rating of 601 versus 600. Did you know that? Somebody got their little rating in there. Has to do with kVA of a transformer and stuff like that, but anyway. Is there a difference between a 600 and a 601 overcurrent device? Other than the 1 on it, there is absolutely no difference whatsoever. Because the accuracy of those devices ain't anywhere close to the 3rd decimal place, not even close. All righty, so let's go on talking about combiner disconnects. Let's see, we're going to talk about some other fun stuff. Let's go back to our list for a second. I'm going to pull up our list. We've been talking about some good stuff, but I want to make sure we hit. So calculating the maximum allowable system, I want to get to that before the end of the day. Hopefully we've been talking about what matters. We talked a little bit about center fed panels, 120%, but we'll talk about that a little more tomorrow in the changes in the code. But pushing for AHJs to approve supply side connections, I think we did talk about that to some extent in that it is important to understand that even though a parallel generator is not counted in the 6-handle rule, it is wired exactly like a service, and it could become a service. And what's wrong with that? And why would that be any different than running a service disconnect on a set of conductors? So let's just kind of turn the whole thing back around the other way and say, wait a minute, you got a jurisdiction that's saying you can't do a supply side connection. But I can do a 200 amp service disconnect off those service conductors, right? Well, yeah, sure. But you can't do a PV system up there. And why not? Because that's upstream of the main overcurrent device, and I can't do that. Well, but I got to have an overcurrent device on that. It's a parallel generator. It's like, so you got to back the truck up and go, I can take any service disc, I can take any set of service conductors on any service in the United States of America, and I can make a connection to those service conductors, and I can run a service disconnecting means off of that service disc, off of those service conductors. Code is clear on that. I can put a 100 amp service disconnect on my, I just can't put anything more than the rating of the conductors. But I can go up to the rating of the conductors, and I can go up to 6 disconnects. Now, at the end of the day, I also have to do a panel schedule, okay, so I can't put more, I'm not allowed to put more load on the service than the service has. And that's clear. So I can't just willy-nilly add service disconnects. But the addition of the service disconnect has nothing to do with the safety of connecting to that wire. We do it all the time. We make service connections all the time. So what's wrong with making a parallel generator connection in the exact same way? Nothing. There is no logical difference between the two. So any logical reason, any logical AHJ that says you can't do it is not thinking logically. They're not looking at the picture, okay? Because then you could just come out the next day and say, oh, I don't want to do a 200 amp supply side PV connection. I want to do a 200 amp service disconnecting means. But when I do my panel schedule, I'm not going to change my panel schedule at all because this is a supply conductor. There's no load. So I don't have to do a panel schedule. You already got the existing loads on the building. I'm adding supply. So I'm done, right? Well, I don't know. What do you think? Logic. This is you can't have it both ways. This is, I'm not adding any load. I'm adding supply. And so all I have to worry about when I'm adding supply is, could I overcurrent any conductors? Well, if I've got a 200 amp service, I can supply up to 200 amps with supply to those conductors upstream of the main service disconnecting means. There's no loads on that circuit whatsoever. Any of the loads are being pulled off the 200 amp overcurrent device, which is fully protecting that. There's no way I can overcurrent anything in the picture. So why shouldn't I be allowed to do that? Well, because it's a supply, or because it's a generator. Makes no difference.
So my experience on that is we've had several utilities. They don't trust the UL listing on the inverter.
Ah, there we go. Now we're getting down to real brass tacks.
And either it's at the grid, either it's at the supply side or it's with battery backup inverter.
Yeah. So if you distrust the listing of the product, but somehow when there's a load there, you don't distrust it, you know, again, we have a logic problem here. And so you can't have it both ways. You can't have it all, you know, any way you want to do it. So that's why we have rules and people have to follow rules. But, you know, you'll find that often the logic is very, very thin on these issues. Okay, so let's see, I don't know. I mean, at the end of the day, the utility has to approve supply-side connections at some level. The city of LA used to not, the Los Angeles Department of Water Power for many years did not allow supply-side connections. It was just somebody in their department said no. There was no logic given to it or anything, even though the code allows it. And so, you know, these, once you boil it all down, you find that somebody's got a misconception somewhere, and they're in a powerful enough position that, you know, they're able to let their opinion stick even though they're wrong. Everyone is entitled to their own wrong opinion, so.
So, you know, right here, the whole San Diego County doesn't allow it, but then you know about the RMA, the Ken Marks renewable meter.
So San Diego County does not allow supply-side connection?
The whole county, every city jurisdiction as well.
As well as the city?
They will if you get a third party.
Unless you get the RMA. Right. And residential isn't allowed. But they have it for $1,300. You could buy you can have them install the renewable meter adapter, which will give you 60 amps of solar. So you need all
So you
that.
can do that, meter adapter, and a 40 amp backfeed breaker, and now you got 100 amps of backfeed on a 200 amp service.
So they'll allow you to do the 40 amp breaker as well? Okay. but they won't allow you to do a supply-side connection.
That was the only option.
Well, they're doing it for you, basically.
Right. Well, I mean, the RMA is a great option when you have service equipment that you don't want to screw around with. And that's totally understandable. But to say that you can't do it, even with listed equipment, is ridiculous. It's absurd. There are lots of service equipment where it's not legal to make a connection in that service equipment. I totally agree. But there's lots of equipment where you can. And you can have a separate box. And my point is that service connections to service conductors are done all the time by utilities routinely all the time. And so what makes this any different? It's a logic problem. It has nothing to do with the technical issues at all. It's people don't get it. They don't understand what they're talking about. So, sometimes we can get through it with logic and sometimes we can't. And that's unfortunate that it doesn't always work that way. Grounding and bonding, we should chat about grounding and bonding, so let's move on. All right. Identification, so we talked a little bit about that. So this is where actually the 2014 code adds this statement here, this is the statement that kills us on grouping, which says that we're not allowed to group our source circuits with PV and with inverter output circuits. And that basically creates a real problem with trying to use the same gutter unless we have a partition, unless it's separated by a partition. So if you're in an area where they have been allowing this and we go into the 2014 code, the local jurisdiction may continue to allow it, but you are definitely now into a new realm that as they learn about that, they may say, oh, you can't do that anymore. So just be aware. All right, there's the cable tray stuff. Let's move on down. Connectors. So it is important to understand that way back in the 2008 code, we added a statement that a connector, if it's rated for interruption of circuit, has to be rated to be taken apart under load without hazard to the operator, which actually, it turns out the N-phase product has been listed that way, or be marked do not disconnect under load. And so most of the products that are out there say this do not disconnect under load instead, and that is allowed. This along with, so in 690.14, it talks about inverters in not readily accessible locations. That's in the 2011 code. It got moved to 690.15 in the 2014 code. Sorry for the moving things around stuff, but basically that talks about inverters in not readily accessible locations, and it says that an inverter in not readily accessible location has to have DC and AC disconnects within site or within the inverter. Okay? So a microinverter is generally, most cases, unless the ground-mounted system is in a not readily accessible location, and therefore has to have disconnects on the AC and DC side. And then there's an exception way down in 690.17 that says that a connector used according to its listing can be used as a disconnecting means. And that puts it all together for a microinverter system. And we essentially have to do all that together. Anyway, there's a whole another thing I don't want to go into right now, but that's how we get microinverters to be installed in the way that we traditionally install them today.
But doesn't the disconnecting means have to be in a relatively accessible area? Because your connectors are not any more accessible than the inverter.
No, it just says typically it have to be accessible at the equipment. So like in, I think it's Article 40, just went out of my brain. Maybe it's 404, talks about air handling equipment, things like that, the disconnect has to be readily accessible to the equipment. That's 440, I think. So what we wrote that's why the section inverters are not readily accessible locations was written in 2005 code. And that was to specifically address the fact that the way the code was written, all your disconnects had to be in readily accessible locations. And now if you put your inverter in a not readily accessible location, what are you going to do? Run wires down the side of the building to a readily accessible location? That's crazy. So that's stupid. So it's got to have disconnects within sight or in the inverter. And so within sight means visible to and within 50 feet, and then, of course, in would be right at it.
Which is not on the roof.
Well, they were within sight of the inverter. That's what it says.
Right, I mean, the idea is to be working on the inverter.
Right. If you're working on the inverter, you're going to have to remove the panel, and whether you disconnect the module before you take the panel off, or you do it after, depends on how hard it is to get to the connectors.
So in 69013, talking about disconnecting means locations nearest the point of entrance, like you have an inverter inside a house. I recently had an inspector tell me that like within 6 inches of entering the house, so like you come through the wall, you have an inverter 2 feet from where it enters the wall, you have to have a disconnect in that wall. Like what would the actual interpretation of nearest point of entrance be on that?
It's subjective, and if they were arguing over 2 feet, that's ridiculous. Yeah. So the point is that nearest point of entry, that is tested all the time with service conductors, because service conductors are supposed to have the disconnecting means of the nearest point. That's where this language comes from, Article 230. So your disconnecting means either has to be outside the building, nearest point of entry into the building. Well, what they do is they go, well, on a service drop, coming off in your weatherhead off your roof, what's the nearest point of entry? Wow, I'm going to put it in the eave in the corner in my attic. No, that's silly. So what they do is they require it to be in rigid pipe from the weatherhead all the way down to the service disconnecting means. And so that's the way they've addressed it. But that's essentially been done by an agreements with the utility companies and stuff like that. So it's not really clear that, so nearest point of entry, that's been accepted as nearest point of entry. So one way around it would be to say, would you be okay with putting in rigid for up to that, if you wanted to go 6 feet or 8 feet? Okay. They should buy off on that. But if you're not going to do that, then yeah, nearest point of entry would be wherever it penetrates and you can physically mount a switch of some kind, which would be within a couple of feet usually. And you hear numbers like 6 feet as being kind of the edge of pushing that limit. Okay, let's see. We want to talk about grounding. So grounding happens after all this stuff. So Part 5 in the code talks about grounding. And there's 2 types of grounding that we have to be concerned about. And the first is system grounding, which is referencing the conductors to earth that are current carrying conductors. And then we have equipment grounding, which also entails bonding. And so we've actually changed the terminology to bonding and grounding for equipment grounding just to make it clear that that's what we're talking about, whereas systems, we're talking about grounding the system. The way it's written right now up to the 2014 code, we're either compliant with 690.35, which is ungrounded systems, or if we're above 50 volts, we're connected to earth somehow. Okay? What's not clear is the how. Our hows are always through our ground fault detection devices. So in order for a ground fault detection device to work, it has to be the source of where ground is. Because it's defining, it's saying, okay, I've got ground here, and I've got my circuits here, and I'm making a connection to earth, or I'm making a measurement to earth at one location. And the problem is, historically, we've treated our PV systems that had like a negative ground, fused ground, we've treated them as a solidly grounded system. That has some real safety issues, which is why we added 3 or 4 safety warning signs into the code to address the silly safety issues we have with that. And it also creates a misconception using white wires. So we've also preached that, hey, you should be using white wires because these are grounded conductors. And according to Article 200, we have to use white. 200.6 says that grounded conductors have to be white or natural gray. And that is a huge problem on a ground faulted system where that circuit is at 600 volts, because that grounded conductor is no longer grounded. It is actually energized conductor. But in fact, you know, the concern that somebody would misconstrue a white wire as being a low voltage or a ground potential, that's a bad idea from day one, because we're actually allowed, throughout the code, we're allowed to run 240 volt circuits that have no 120 volt loads. We're allowed to run them with a cable that's a black and white wire. So if you know somebody who's in the habit of touching white wires, then they will get a Darwin Award one day when there's a fully code compliant system where it's got a white wire that's running at 120 volts to ground.
Bill, as far as bipolar systems, you know, in the time that I've done solar, I've never seen one.
Yeah.
Is there, what's the advantage? Does anybody make equipment for them, and
Good
why
question.
would you use it?
So bipolar systems deserve our pity. They have emotional problems, and they really need help. Counseling, possibly, and medication. But well, we did come up with a proposal for the 2017 code that bipolar PV systems, when used with energy storage, shall use lithium-ion energy storage systems. We figured that that would help. I don't know. These are very, very, very bad code jokes. This is where it goes. So anyway, bipolar systems have not been built for years and years and years. Advanced Energy called their system bipolar systems, and in the international world they actually are. According to our code, the center tap of a bipolar system is solidly grounded, and theirs is not, because theirs actually separates it into 2 separate circuits and all this kind of stuff, which is in Article 690.7, which is in 690.7 anyway. But bipolar systems, we've kind of reorganized that to include the advanced energy style system, because we're going to see a lot more of that in the future. In fact, Refusol, who Advanced Energy bought, and then they all went out of business or got out of the market, they had 2 500 volt circuits that were separate circuits coming into their inverter, and then they put those circuits in series, and they created, it was a bipolar-esque system as well. It's very similar to the Advanced Energy, just different way they did the control on it. But the fact is, what's that? A bipolar system is where one pole is operating above ground voltage, and the other pole is operating below ground voltage. And they're centered around ground. Okay? So pole to pole, the Refusol system was up to 1,000 volts. The Advanced Energy system was up to 1,200 volts. But pole to ground on either side, on either one, at most could ever be 500 volts for the Refusol or 600 volts for the Advanced Energy. It's a split-phase DC system, exactly right. It is the DC analogy of a split-phase AC system. Here and then there. Go ahead.
But that only happened within the inverter wiring itself. It wasn't external, and you could never run an odd number of strings on that.
Not unless you had their RPT. If you had the RPT is out in the array, and so all the wiring was external. And so, yeah, so there's in this done completely safely, but the code didn't specifically address it. So now the code addresses it more accurately, and there's nothing wrong with having a bipolar system where half the array is operating at above ground voltage, and the other half is operating below ground voltage. And you didn't even know that your non-isolated inverters is exactly that. Okay, So your non-isolated inverter systems, if you've got a 600 volt DC input to a non-isolated inverter, which everybody is doing today, when it's running, test voltage of the DC positive to ground, test voltage of the DC negative to ground, and you're going to find out, guess what? They're identical. One's positive and one's negative. Why is that? Because it's running into a grounded transformer. Okay, the grounded transformer is providing the center tap of that circuit, and it regulates that circuit has to run on either side of ground in order to work. That's because it's non-isolated. So it has a direct connection to earth through the transformer, grounded transformer. Okay, so we can riff off of that and start splitting the array up, and we could actually run a residential PV system today at 1200 volts pole to pole, 600 volts to ground. Totally legal. Okay, nobody's doing it yet, but they might. But like I said, we're going down in voltages with residential rather than up in voltages.
What was the supposed benefit of that?
Higher voltage on your inverter. So the holy grail of an inverter is to be able to synthesize a sine wave in one step. Okay? To synthesize a sine wave in one step, the higher the voltage is, the easier it is to do. Okay? So if you're synthesizing a 240 volt signal, what's the peak voltage of a 240 volt signal? You got to calculate that, and then you got to be above that. Okay? And so you're at 480 volts, even 1,000 volts not high enough. Okay? So at 480 volts, you still have to have a converter in the circuit. And so that's the big push to 1,500 volts, because I want to be able to go to 480 volts in one step. Okay? And it's basically how Advanced Energy got to 480 volts in one step. They did plus or minus 600 volts to ground. They did 1,200 volt pole to pole on their inverter, and they got to 480 in one step. So,
Going back to your wiring, so you said you can use white and black on a 240 split phase?
in the code, we can wire a hot tub, for instance. And if it's all it's got is 240 volt load, it is legal to take a multi-conductor cable that all it's got is a black and a white and a ground. And we can run that to that hot tub.
So then my question is, can you, this is for solar, do they need to be different colors?
Yes. In fact, with the exception of multi-conductor cables, which would be allowed in Article 200, we want them to not be white. So we basically want to do our wires. We're going to consider a functionally grounded conductor as not a solidly grounded conductor. So the way we stated in the 2017 code is that only solidly grounded conductors shall be white.
So sorry, I was going in another direction, but could it be two blacks or two reds? Or does it have
Could be two blacks, could be two reds. Then we get into identification. Okay, so throughout the code, if you've got different phases, you have to identify the phases somehow. Okay, so we use black, red, blue. We use, the phase colors, which are not in the code but are just industry standards. Or we use phase tapes. We use numbering. We use lettering. Those are all allowed methods of determining differences between conductors. So throughout the code, we're not allowed to run a whole bunch of black wires to a box in the code. That's not allowed. We have to identify those conductors. But in the PV world, nobody was reading the rest of the code, so they're like, I just got a bunch of wires. They're USE, they're all black. I can't do anything with it, so I got this bundle of black wires. So which one goes to which? I don't know. Just start terminating them. I don't know.
What about on the DC side if you have like 4 strings coming in?
So if they're all black, they could be very common. You could have all black conductors coming into an inverter. You're going to have markers on those wires. So you're going to have 1 plus 1 minus, 2 plus 2 minus, 3 plus 3 minus, whatever it is, Or you could use different color tapes. Those would be all acceptable, and Article 200 allows us to actually color black wire that's smaller than number 6, because it's an exception for PV systems. So, okay. So system grounding point is at the ground fault protection device. I think we talked about that. And then there's talk about equipment grounding. And so this is where we get into all the arguments with, you know, the big issues on the table with AHJs are generally around how do we do proper bonding and grounding of PV modules, arrays, array structures, you name it. These are all valid questions and important questions. And for years, grounding and bonding has been poor in the PV world, quite frankly. And so we had guys like, you know, Wiley Electronics came out with the Weeb, and everybody talked about the Weeb because it was fun to say. I mean, Weeb, I mean, it's just kind of like dweeb, I guess, you know, it's just like, so it's fun to say. And so then the Weeb got vilified as being, oh, well, it's got to be in the installation instructions, and boy, you can't trust those things, they never work, and yeah, if you had to use them more than once, and they just, you know, one thing after another. When the darn thing was just trying to fix a really simple problem of creating a bond between two pieces of aluminum, where aluminum doesn't bond very well. Okay, so, but everybody got all worked up about it, and articles were written and all that good stuff, and so that really kind of snowballed into what we call UL 2703 today. So UL 2703 was written originally around grounding and bonding of PV arrays and structures and modules, and how do you do all that? And it's still in the process of getting worked out, a lot of the details. It's been in play for a little over a year now. And there's quite a few products out there that have been evaluated to it, and more need to be. And so, you know, over the next year or two, that whole world is going to get a lot better, a lot simpler, a lot more straightforward. And so guys like Snap and Rack obviously have products that are available, listed and certified 2703, and have the documentation, stuff like that, and that's all good. Not all jurisdictions have accepted these certifications and all, and so one of the big deals going on at LA County is in fact, there's a summit on UL 2703 the end of this month, is that right? The 2703 summit. So you had the climate summit, now we have a UL 2703 summit. I don't think Obama's going to show up to that, I'm just saying. But it's important to the solar industry to make sure that we do a good job with grounding and bonding. It's gotten way overcomplicated, people gotten, you know, I think bent out of shape with it. So hopefully we'll get a little bit more kind of sanity to the whole process, and the listing process will make it a lot cleaner and a lot clearer. And at the end of the day, we just want to take this off of the plate of the contractor or the installer and the AHJ as a major problem. We just want to make this done and solved. You install it. There's one way to install this product. You install it with all these features. And if you don't install it with all these features, it essentially falls apart. I mean, that's the way I like to see a system go together. You install it one way, and you don't have 3 different ways that you can install it, and you can leave stuff out. Because every time you have a system that you can leave stuff out, people leave stuff out, right? So, you know, that's one of the problems is the AHJs are going, well, how do I know that they put all those little washers? You got to do this, and then this, and then this, and then this. And it's like, well, you have no idea. There's no way of knowing. Unless you tore the whole system apart and put it all back together again. Does that make any sense? Of course not. Okay, so let's have a system that just goes together one way. When it goes together, it bonds itself. We have one conductor, comes off an array section. That is the equipment grounding conductor for that entire section. There is no reason to run copper wires all over aluminum equipment, which has always been a bad idea. And then all the stupid things that are out there. Anyway, don't get me started. Sir?
How can AHJs not accept something that's already been certified? And I mean, what's their rationale, or a county saying, well, we don't accept this, you have to go do it the old way? What's the rationale behind that?
The code encourages AHJs to accept certified equipment. It does not require them.
Well, then how do they, what's their basis for approving it if it's not, if it's, in other words, do they require some sort of a personal certification?
No. So what Article 90 says is that testing laboratory, it requires that the local jurisdiction approve all equipment, okay? And that when they approve equipment, that it shows it's been tested to the appropriate standards, whatever those standards might be for any piece of equipment. And that there is a process called recognized testing laboratories. This is all in 90.3. It says there's these recognized testing laboratories that are out there, and that their purpose is to certify equipment to these existing standards, and that AHJs should accept equipment that has been certified by these recognized testing laboratories as sufficient for testing. But the ball is still totally in their court, okay? Most jurisdictions will do that. Now, where it becomes a little bit interesting is that jurisdictions are also on a lot of these standards committees. In fact, they're required to be. So on UL 2703, UL 1703, 1741, we have authorities having jurisdiction on those standards committees to help balance the committee and provide input. And for instance, 2703, County of LA has representation on that committee. They still have lots of questions. And they have opinions about what 2703 should say, okay? And why do they go against it? Sometimes it's just a bad experience. Somebody had a bad experience, gave them a bad taste in their mouth, and so now they're mad at the world, and they're mad at the PV industry, and they're taking it out on the PV industry. Those things happen, and that's unfortunate, and that's why we have to be very careful about how we, our first impressions and all that. But at the end of the day, once it goes through a certification process, it's a lot stronger and much more difficult for an authority having jurisdiction to create a big stink about it. And at some level, political pressure can and has been brought to bear on these issues where, somebody said, well, I'm not going to accept that, and it's like, well, the mayor just said you are going to accept that, sorry. And then they have to shut up and sit down. It's not the best way to deal with these things, but it occasionally has to get there. 2703 is a new standard, so it's got kind of the ugly adolescent period right now, and actually it's not perfect. And in fact, one of the big issues and concerns that the city of LA has brought up is bad installation instructions, and that's a fact. There's a lot of bad installation instructions out there, which hurts everybody. So get it up to speed, and so the good thing about having them in there and them being concerned about it is that that we're seeing better installation instructions and stuff like that, and this summit will hopefully bring this thing to the point where the County of LA is going to be much more accepting. And at some point in the future, hopefully within a year or so, when somebody comes across their desk with a UL 2703 certification from Intertech, UL, CSA, whoever's approved to do it, there's no questions asked. We're not there yet with that jurisdiction and some others as well. Let's go ahead and take a quick break. I know we've been sitting for a long time. Let's take a 10-minute break, and then we'll finish up the afternoon and then have happy hour. So grounding and bonding, at the end of the day, and we did do some rewriting in 690.43. I think we did some nice cleanup. But when we leave the array, the equipment grounding conductor is going to go with our current carrying conductors. But within the array, the equipment grounding conductor is really allowed to take whatever kind of path it has to in order to do bonding and stuff like that. An equipment grounding conductor, in fact, in Article 100, in the definition section, says that it can perform the function of bonding. And the term bonding means that we're making two pieces of metal, two conductive things at the same electrical potential. Okay? So, and the reason that's important is that if you got things that are metal and they're next to one another, the worst possible thing is that one thing be energized and the other thing be at ground potential, right? Because now you've got a situation where you're steadying yourself on the roof or something like that, and you grab one, you grab the other, and now you become the path through your chest or whatever to complete the circuit. And so that's why bonding is a very critical safety issue, to get everybody anything you can touch, or it's accessible at the same electrical potential. And then we take that thing that's all at the same potential and we make it ground potential by connecting it through an equipment grounding conductor to earth. Okay? And that way, if we have one piece of equipment connected to earth here, and we have another piece of equipment connected to earth there, if I happen to be able to touch both of those pieces of equipment at the same time, I don't necessarily have to have a bonding jumper between both of them this way. I know that I'm protected to earth down there. I could have a chimney or a vent pipe that's metal vent pipe. And that's something that often can be easily touchable from our array, which could, if these things are different potentials, could be a real problem. So that's a little bit about equipment grounding. And as I said, things that kind of got screwed up a little bit with 47D, and we'll see that in a minute. Size of equipment grounding conductor, basically the easy way to think about it is that we're allowed to use table 250-122 for our size of our equipment grounding conductor, which is based on the size of the largest overcurrent device, and then it goes into a lot of detail about what if you don't have an overcurrent device and what you would use for that. But suffice it to say that when you're worried about the equipment grounding conductor size, the easy answer is on small circuits, 30 amps or less. So if you're using 10 gauge conductors for your current carrying conductors, you're always going to have the same size equipment grounding conductor. Even though, if you do the calculation, you could live with a smaller size. Smallest size allowed is 14 gauge. But here's the deal. Throughout the rest of the code, if you've got a 30 amp circuit, you're going to have a number 10 equipment grounding conductor. And so if you try to go buck that, this comes down to working with AHJs. Even though the code would allow you, if you go through all the exceptions and everything like that, to put in a 14 gauge equipment grounding conductor, it will raise a question. It will raise a question every single time because it's very obvious to an inspector that knows anything about electrical. And so now you're going to have to go through the long discussion. Now, if you want to have the long discussion and you want to use this as a teaching moment, and you're really clear on how all the exceptions work and where to go, then you're feeling lucky. And so if you're feeling lucky punk, then go for it. But in general, it's better to avoid questions than it is to raise them. So that's the easy. So you see here, we can use number 10 copper as an equipment grounding conductor up to 60 amp overcurrent device. Okay, well at 30 amps, it is the same size. And so at 40, 50, and 60 amps, it is undersized. And so that's the break point for undersized, anything above 30 amps. And so we're using a much smaller equipment grounding conductor because the equipment grounding conductor, the only thing that equipment grounding conductor is being called upon to do is to carry current back to the overcurrent device to trip the overcurrent device. And so these calculations are based on fault current calculations and undersizing or downsizing those based upon the allowable fault current that would typically flow in these types of circuits and the minimum size conductor that would not fuse and come apart while the overcurrent device is trying to do its job. So that's where all that kind of comes from. Okay, grounding electrode system. So the code talks about it, and so we'll briefly talk about it here in 2011 code, 2014 code, a little bit different but similar. So there are three options currently in the code for how we would connect the the DC grounding electrode system and an AC grounding electrode system. Okay? Now, it's predicated on some errors in how we've done things in the code, so let's just set that aside for a moment. Again, if we were a solidly grounded PV system, then that DC ground it's a DC grounding electrode conductor that goes from our negative to ground. Now, with a ungrounded system, we still got to know where ground is, and so that we get into the code on how do we determine it, and the code allows in certain situations the equipment grounding conductor to be used as determining where ground is. But the way the code is written right now, 2011-2014 code, if we have a grounded DC system, we're going to supply a DC grounding electrode conductor. It's going to go from wherever the circuit is connected to earth or reference to earth, and that's always going to be the ground fault detection device. And that ground fault detection device is, without exception in grid tie systems, at the inverter. And the only exception to the inverter is that our battery-based systems often do the ground fault detection at the charge controller or at a device next to the charge controller. So battery-based systems can be a little bit different, but they're still very similar. The device may either be outside the unit or it might be in the charge controller. Most of our charge controllers nowadays have the ground fault detectors in them. And at that point, that establishes the grounding electrode conductor. That grounding electrode conductor is supposed to go to ground, and there are three options on how to do it. Option one is to go directly to the grounding electrode, and that grounding electrode could be any of a whole bunch of different things, including UFR grounds and ground rings and all that kind of stuff. The second is, number one is where it goes to, let's say we drive a ground rod. So let's say we drive a ground rod at our inverter, and we take our grounding electrode conductor to that inverter, from the inverter to that grounding electrode. Then it still requires us to connect that grounding electrode over to the AC grounding electrode, okay? Because now you've got two different electrodes on the same structure, and the reality is you're not allowed to have two different electrodes on the same structure in general. There's a few exceptions, but we'll say in general. And so you're going to create a grounding electrode system. So in reality, you really didn't do anything differently. All you did is put one near the inverter. Number two is really the same as number one, except you're going to the same electrode. So let's say you have a driven ground rod or whatever it is, then you're going to take your grounding electrode conductor over to that driven ground rod, which is where the grounding electrode conductor from the AC service is also tied into. That's fine too. So whether you have one ground rod or 5 ground rods or a ground ring or a UFR or anything like that, you've got what's called a grounding electrode system. And all we have to do is make a connection to that grounding electrode system. As long as the cables and the wiring between all the ground rods and everything are sufficiently sized, any connection to that grounding electrode system is connected to ground. There's no differentiation doing it at the rod versus at the cable or anything like that. It's all the same. Which is good news for us, especially if we're working inside of a situation where the grounding electrode is hard to get to, or maybe it's buried, but we have a grounding electrode conductor staring us in the face. Because if there's a single grounding electrode, the code says that thing could be as small as number 6, and that's connected to ground. So I can actually I can take my DC grounding electrode conductor and connect it directly to that cable, and that's connected to the earth. And there's no question about that. Some inspectors will scratch their head on that one for a while, but you got to think about it for a minute. And the grounding electrode conductor is earth, and it's part of the grounding electrode system. So I can make an irreversible splice to that, and that's as good as anything. In fact, I should be able to make any listed splice to that, but that's another story. I'm not going to push that one too hard with an inspector because I'm already stretching their brain anyway.
What do you have when you have a situation with a ground mount that's considerably away from where the house is? Right. What do you do in that situation?
So it's a separate structure, and it's not super clear in the code until the 2017 code. So 47D, which we're getting ready to come up on, 47D, which we're getting ready to come up on, basically says, we wrote that originally to say that if you had a separate structure, that structure would have to have, and a PV's mounted on it, that structure's got to have an electrode. And the equipment grounding conductor should be tied to that electrode, the local electrode. That doesn't prevent you from being required to take that equipment grounding conductor back over to the house if that's where the AC service is, but you want to have it connected to the local electrode as well. You don't want to be separate because step potentials and things like that could be different from the voltage at the house, and so it's better to have something nearby, which is the same reason why you have to have an electrode for any structure that has electricity on it. It's a local electrode for step potentials, nearby potentials, and things like that. And so we put that in, and the 2008 code panel screwed it all up. And they rewrote it, and they screwed it up, and it turned into something that you can't even understand. But that was the initial intent. 2017 code goes back to that initial intent that says, if you got any structure with PV on it, it's got to have an electrode. If it doesn't have an electrode already on it, then you install one according to Article 250.
But it's still got to be wired back to the AC electrode.
The equipment grounding conductor must eventually be tied to that electrode system, the local electrode system, and that's the key. But it doesn't have to be done, which is what 47D says right now, it doesn't have to be done with a grounding electrode conductor. That's silly. Why would you use a grounding electrode conductor to connect to equipment? It's equipment. You use equipment grounding conductor for connection to equipment. I don't know why that's such a hard thing to understand, or why the people in the 2008 code screwed that up so bad. But you use an equipment grounding conductor to connect the equipment, and they eventually makes it to earth in the normal path that an equipment grounding conductor takes. And if you've got a normal equipment grounding conductor connection over at the house, which is, let's say, 100 feet away from this ground-mounted structure, then you have to come up with a way to make a connection from the equipment grounding conductor to that local grounding electrode. Okay, well then how are you going to do that? Well, there's going to be some kind of a grounding electrode conductor come off of that electrode that you drove. Let's say you drove a ground rod at that equipment, or maybe it's a pole mount. Maybe the pole mount's 8 feet deep. If it's 8 feet deep or more, it's a grounding electrode all ready to start with. So all I need is a bonding jumper to run from my equipment grounding conductor to that pole that's 8 feet in the ground. I've bonded it to ground. Okay, so if it's not 8 feet in the ground, let's say it's 4 feet in the ground or 5 feet in the ground, okay, now I'm going to have a driven ground rod, and I'm just going to take an equipment ground, I'm going to take a grounding electrode conductor, and I'm not going to take it to the frames of my panels, which is the way it's written in 47D. I'm going to take it to whatever's the easiest way to connect to the equipment grounding conductor. It's an equipment grounding conductor. So I can, if it's a bare copper wire, so let's say I ran a bare copper wire for my equipment grounding conductor in my array, okay, fine. All I need is a split bolt, connect the number 6 to that thing and go on down. Because anywhere on the equipment grounding conductor and anywhere on the frames are all bonded together, because they're all one electrical unit, and I can connect that to the grounding electrode. Okay, so the common AC and DC grounding electrode is where I take our DC to ground here and our AC to ground there. The grounding electrode go to the same location. And then we have something called a combined DC and AC electrode. And this kind of got some folks in the code a little upset with us. But we said, well, wait a minute. You know, we've got an inverter, and we've got a terminal in the inverter, and we're going over to the main service panel, and we've already got to have an AC equipment grounding conductor in there for the AC circuit. And now you're telling us we've got to do a grounding electrode conductor from the DC side over to there. And they're both starting and stopping in the same location. They're both connected to the grounding electrode. So why don't we just take the larger of the two and call it good? And it basically is a combined, it does both the AC equipment grounding conductor and does the DC grounding electrode conductor. So that's what number 3 was. We got it through. We pissed a few people off in the process, but that was intended to not have just an extra wire that really isn't going to do anything. If you're already going to run a number 8 from your inverter to your main service panel, there's no reason to have a number 12 also doing the exact same thing. It's just an extra piece of wire. And if it's 5 or 10 feet long, I'm not going to argue with anybody about it, but if it's 50 feet long or 100 feet long, that's a real pain in the butt to carry another conductor through that same raceway.
Why do you have to have 2 ground rods?
2 what?
In San Diego County, they require that we have 2 ground rods. We have to have ground,
Oh,
and then we have to have one 6 foot away from that ground rod.
it has nothing to do with PV. It's a loophole in the code. So, because ground resistance measuring devices are expensive, what the code says, if you have a driven ground rod, if the resistance to earth of the first driven ground rod is more than 25 ohms, you must go 6 feet away from that, which is outside the influence of the first ground rod, drive another ground rod, tie the 2 together, and the sentence stops. Doesn't say retest and see if it's above 25 ohms. So basically, it is a required out for doing ground resistance testing. Okay? Right. That's right. That's all it is. It's a loophole. It's a complete loophole because the second ground rod is probably no better than the first one. It might be. It often is a little better. But if you're in a really, really bad grounding area, the second one's going to be no better than the first one.
So the wire, it doesn't have to be a continuous wire from the panel to one ground rod to the other. You could just, like if I have an existing ground rod, I can put another ground rod, and then I can just put an acorn nut and put a jumper from that ground rod to the other one, and I'm leaving.
That's correct. Absolutely. Because often in a retrofit, it's not going to have one, right? You know, you're not going to have a continuous wire. So you've got an existing ground rod, and it's already got an acorn on it from the main service. And so now you're going to have to put another connector on there because these connectors are only designed for one conductor. And then you're going to have to go from that one to the new one.
Right, but a jumper's sufficient, because I've had that do the argument where they're like, well, it's supposed to be a continuous ground, but then it like makes for a lot of work. So.
No, there is no requirement in the code for irreversible splicing on the connections to the grounding electrode system. So conductors in a grounding electrode conductor, if you splice it, has to be irreversible, okay? But the connections to the actual grounding electrode do not have to be. In fact, they're never irreversible except for things like CAD weld and stuff like that. So where you've got exothermic welding, you know, obviously that's irreversible, you know, and far better, quite frankly. Okay, so that's why we say whenever you hear unspliced, irreversibly spliced, things like those terms, you're talking about a grounding electrode conductor. If somebody tells you an equipment grounding conductor must be irreversibly spliced, they don't know what they're talking about, because equipment grounding conductors get spliced all the time, often 5 or 10 times on the same circuit. So, and that's totally legal. Okay, so, sir.
Our standard operating has always been if we have a DC grounding electrode in the metallic raceway, it always gets an IGB.
Always gets a what?
A grounding bushing, because it is a grounding electrode. So whether it's a concentric knockout or we've knocked our own, it always gets one. Is that accurate?
Good practice. If it's a metal raceway, then you should not only bond the bushing, but you have to bond both ends. Now, I don't think it's appropriate to say if you didn't have concentric knockouts, does the code require you to bond? I don't think it does. It requires you to bond both ends of the raceway. Both ends of the raceway are already bonded to the enclosures. If they're metal enclosures, then I don't think that would be a requirement. But you would still have a jumper. You would still probably have a jumper from the enclosure to the grounding electrode conductor. That would be an alternative. The way you're doing it is, belts and suspenders. So, and again, with the number 6, going through, continuously through those things can be a real pain sometimes. So sometimes, just because the physical way it's wired, it's better to have the grounding electrode conductor just go straight through and then use a jumper to come off of. And the question is, that jumper does not have to be irreversibly spliced, because it's just a connection to both ends of the raceway. Yeah. Right. And these things were all already functionally grounded systems anyway, so they weren't solidly grounded, and they never really required the DC electrode anyway.
One other one that we've had is about landing the grounding electrode conductor coming from the inverter on the bus bar in the main panel.
Yeah. That's allowed under number 3 here.
Well, they didn't interpret it that way. They say that's, the AC equipment, it needs to be, because later on, there's also the part, I remember the code, where it needs to be irreversible and it needs to be serviceable. But it says you can, if you have to service, you can allow a jumper at the point of service to land it in the main panel. Anyway, it's
In 250 it might say that, but in 690-47C3 it says specifically that it can terminate in the AC equipment supplying the inverter. That's the 2014 code. So the 2011 may not be that specific. I'll have to look it up.
okay.
I don't think it was.
Well, in 2014, they're still interpreting it. We've had it where they say, no, you can't do it. And they're saying the inverter is the AC equipment, because otherwise it should say the main panel. And I don't know if there's any.
Okay, I'll just pull up what it says, but the argument for making the connection in the service panel serving the inverter is technically tight as it can possibly be. There's no reason to require anything further than that. It's also things like separately derived systems that's allowed to be done with, and other things like that. So, but let's just see. I'm just real quick reminding myself what it says in. Lots of changes. So this whole section turns into like 2 lines. Basically, for a PV system, the key is that any structure that's holding a PV system has to have a grounding electrode system. Okay? If you don't already got one, you put one in. If you already got one, you already got one. Okay? Then your equipment grounding conductor, not any of your circuit conductors, your equipment grounding conductor gets connected to that. Now your equipment that you're using may have all kinds of other things that it's got its own equipment grounding conductors, and they all have to go to their same place. Okay? The grounding electrode conductor would only be required, and is only required, it's more than a couple sentences, but there's also a sentence that talks about only solidly grounded systems shall use a DC grounding electrode conductor. And those, so the only thing that's allowed to be solidly grounded in the 2017 code are circuits that are not installed on buildings and no more than 2 strings, period. That's the only thing allowed to be solidly grounded. Everything else has ground fault protection, and everything else is functionally grounded or ungrounded, and does not require the grounding electrode conductor.
What's the code on installing PV on metal roofs and metal buildings?
That's always fun. Do the best you can with what you got. How about that? Are you worried about lightning? Worried about the inspector. So have they raised the issue yet? This is one of those things where don't ask, don't tell really helps. Don't raise an issue that you don't have a really good answer for. Because metal roofs are extremely difficult to bond to. In most cases, it will avoid the the warranty of the roof, which is the whole reason the homeowner or the building owner put the metal roof in the first place. It's a very good roof, and they wanted a really good warranty, and so avoiding the warranty is a real problem. The only technical way that I know how to do a metal roof bonding is to actually connect under the ridge cap, okay, to put some kind of bonding lug under the ridge cap and basically bond all the pans together along the ridge cap. The problem with that idea is that's great for a pan that's continuous from ridge to soffit, but what about bigger roofs where it's not continuous, and now you've got pans that are lapping one another? That's not a good electrical connection. So then now you put lugs along the ridge and you put lugs along the soffit, but then that's going to stop junk. I don't know. It's going to be really difficult to do that in any kind of good way. And then that still doesn't address what if it's a really big metal roof and you got 3 pans in a row. The middle pan you can't bond. So you're hoping for a metal structure at that point. If you're connected to a metal structure underneath, I'm not worried. There's so many fasteners in that metal roof that it's going to make a good electrical connection to earth through the structure of the building. With wooden structures, it's a different story. And at the end of the day, there are no good solutions because nobody's bothered to deal with it. It's not there's no market. There's no way to deal with the market. The only folks that have really ever even thought about this beyond PV have been lightning protection people, because metal roofs can cause some real problems with lightning protection. So, so it makes all the sense in the world with a lightning protection system that you're going to run air terminals across the ridge of your roof, that you got to bond to that metal roof.
Up in our area, the metal roofs are very, very popular, and they don't seem to be concerned about lightning at all. They're just a plain metal roof.
Yeah, and they're over wood. Yeah, and so then the question is, if you're in a high lightning area, that's a little scary because it could get energized and then arc to ground or something like that. But yeah.
Sometimes they're not occupied buildings. Sometimes they are, but sometimes they're not.
Question in the back or comment?
I was just going to ask, wouldn't it be fair to assume then if say the pan became bonded to the roof, became bonded to the system, wouldn't it also then, by definition, be bonded to the equipment grounding conductor and be sent to ground?
That's why I say if you've got a metal structure underneath the metal roof and you're using metal fasteners to hold this thing down to the metal roof, the metal roofing to the metal structure, I'm pretty confident that they're going to have a good connection to earth through that metal structure.
Even if it's just a properly installed PV system that has a good connection to ground, and your cam pierces the paint and becomes bonded, well, that whole pan then becomes...
Yeah, you got to be really careful about what you're saying right there. Because the problem is that you just said that I broke the coating on the metal roof. And see, S5 is very, very, very careful to say that they don't break the coating on that because that would void the warranty of the product, of the metal roof. So you can't have it both ways. Now, the reality is you probably are. And so we can say that without being S5 distributors. And so the likelihood that you're going to create a reasonable connection with all the clamps you got to put on the roof is probably pretty good. But you can't say that in public. You can't say that to an inspector, because the inspector then picks up the phone and calls the manufacturer of the roofing company, and they say, well, I just talked to the roofing company, and they said, if you break the coating on our thing, that warranty's shot. So I'm going to notify the homeowner that you just killed their warranty. It's like, oh, that's a whole bunch of words that I don't want to have talked about, you know.
But if your array is an isolated item if you're attaching it to, let's say, a standing seam, for example, and you're not damaging the integrity of the coating, you still got number 6 that hits every rail and goes down to electrode. So,
Oh, absolutely. And you can argue that, you know, if you're saying that the coating on the roofing is intact, then it's an electrical isolator. And so if you have a metal roof that has no coating on it, bond away, right? There's no warranty to worry about, bond away. If you got something that's got a coating on it, then my argument would be it's isolated. It's not a conductive coating. I don't have to bond to it. Just don't, well, and don't ask too many questions, and do not talk to the manufacturer of the roofing. And don't ever, and see, here's another problem. We had a system where we had to rip out all the bare copper conductor. This is on a very large rooftop system. Had to all be replaced with bare aluminum conductor. Because just the dripping off of the copper conductor voided the warranty of the roofing. So they had to rip it all out. Okay, so where were we? Having fun on grounding. What a blast this is. Okay, let's see. I think AC equipment grounding conductor should be permitted to be the ground fault reference. That's in the 2014 code. Again, we simplified it further in the 2017 code, but and also new sentence in the 2014 code for ungrounded systems, this conductor shall be sized in accordance with 250.122, not 250.166, and shall not be required to be larger than the largest phase conductor. So that way, for an ungrounded system, what that's saying is that your equipment grounding conductor can be used, your AC equipment grounding conductor can be used as your conductor for ground fault detection and all that, and you don't have to have a ground fault, or you don't have to have a grounding electrode conductor in that. And this always goes down better during Halloween, but the auxiliary electrode keeps coming back to life like a zombie, and which has frustrated me very much. But it says an exception to is still there, and it says an additional array electrode shall not be required if located within 6 feet of the premises wiring electrode. This is definitely open to interpretation, but my interpretation is the right way to talk about that is that since I wrote the original proposal that became this mess, is that any PV system mounted on a building that's already got a grounding electrode is already within 6 feet of that electrode. Okay, because the whole building is considered within 6 feet of the electrode, because it has to be within 6 feet of the building. Meets this requirement, and no additional electrode is necessary. But that's not the way it's interpreted by a lot of folks. But that's what I believe we should use and get through. The problem here is that this was not in the 2011 code. So the California code, the 2013 California code, doesn't have it in it. But guess what? It's in the 2014 code. So guess what? It's going to be in the 2016 California electrical code. So it's going to go back in there. It's going to create all the same problems it did before. And exactly. That's a problem. Okay. This is talking about signs and stuff like that, something that maybe some folks don't know, that with standalone systems, we're supposed to have a sign on the house, on the building. This has been there for a long time. Must have a permanent plaque at a readily accessible, readily visible, not readily accessible, readily visible exterior location, indicating the location of the standalone disconnecting means and the structure, and that the structure contains or has a standalone system. And this is primarily for emergency shutdown, things like that. a lot of our standalone systems might have a power shed or something like that, where all the power goes into the power shed, and then there's a feed that comes from the power shed to the house. And so this sign you'd want to talk about where the disconnect is coming out of that power shed, so you can cut off all the power to the house in the event of emergency. Yeah, so a standalone system is a system that operates independent of the utility. And so a battery backup system is a system that is interactive, but when the utility's gone, is running in standalone mode. So it's 2 modes. Okay. Okay, we got about 8 minutes left. I guess we can talk a little bit about the 120% rule. We can go to that. And here's where Mr. Wiles wrote his article and kind of threw everybody into a tizzy on this one. It says the sum of the ampere ratings of overcurrent devices in circuits supplying power to a bus bar or conductor shall not exceed 120% of the rating of the bus bar or conductor. Well, the problem is that it's a thermal issue with bus bars. It's not an issue at all with conductors, because it has to do with an enclosure, a panel board that has a bunch of heat being created by circuit breakers. And so the 120% rule is talking about, well, how much heat are you allowed to add to this panel board, which has been evaluated for certain things. And so the 120% was a fudge factor that was only allowed to be used for residential without any respect to where the breaker went relative to the service utility feed. Okay, so this was an exception, 690-64B2 exception, and it was in the code from 1989, I think, up till 2005. In 2008. In 2008, we put in, after many attempts, a proposal to get the 120% rule extended to commercial. Okay, this is an exception only allowed for dwellings. Okay, and so it was allowed so that we didn't have to mess with somebody's service panel. A 200 amp service panel, we could put a 40 amp breaker in. 100 amp service panel, we could put a 20 amp breaker in. 125 amp panel, and you get the idea. So anyway, in 2008, we said, okay, we want to get this through for commercial because we had some crazy stuff going on in commercial. I remember clearly a system in New York was a 2,000 amp service, and they were going to put a 20 amp single phase inverter on a 2,000 amp service. And the local inspector, honest to God truth, wanted the service to be upgraded from 2,000 amps to 2,020 amps. It's like, are you freaking kidding me? I think we can use a little engineering judgment here. But you know, it was a major issue. And so it's like, well, this is silly, it's stupid. So then we said, okay, well, how do we get this through? Way back in the mid-90s, I came up with the idea, well, what if we require the breaker to be at the opposite end from the main utility feed? At the opposite end, it always subtracts current. And so it's only good, and there's no way the bus bar itself can ever see over current. And so we kind of had that one in the back of our pocket, and we tried it a couple times. In 2008 code, it went through. But the funny thing is, when we got the story back, the guys in the panel board section that were reviewing this actually didn't approve it because of our great idea of the opposite end. They reviewed it as, hey, you know, there's enough fudge factor in it, we'll let it slide. And so that's the way they approved it. But then now we got stuck with this great idea that I had, which was the opposite end, which is still a great idea to do it at the opposite end. But then along came the reality that, well, we got these center-fed panels out there, and these are pretty darn common on the West Coast. They're not even in existence on the East Coast, but they're very common on the West Coast. In fact, the guy I was talking to on the East Coast, I had to like email him a spec sheet on it because he'd never seen one in his life, and he'd been an electrician for 50 years. So anyway, So we get, so this language went in, but it kept the language of bus bar or conductor. And so that's where we got into trouble, or potentially it's just a bad interpretation of it, that somehow if you've got an overcurrent device from a PV system and an overcurrent device from the utility, that the wire in between the two, with no loads on it, that the wire in between would have to be sized at 120%, which is silly. Because the whole reason it's required in a bus bar is because we got loads in between and there's all this heat being generated in the panel and all that stuff's getting kind of all stuck in there. Whereas on a conductor, it's just a conductor, and last I checked, you can flow current in one direction at a time. You cannot flow current in both directions at the same time. It's just physically impossible. Maybe at different frequencies you could do it at opposite directions, but that's weird. Okay, so for a circuit, electrical circuit, current either goes this way or it goes that way. Power either goes this way or it goes that way. And so the 120% rule doesn't matter at all for conductors. The 2014 code makes this very clear, and what it does is it splits this section. Instead of talking about bus bars or conductors in the same breath, it talks about feeders, it talks about taps, and it talks about bus bars. So it breaks it into 3 different categories and makes it clear how we work with a feeder, which is a conductor that runs from a service equipment to a load, or to a load panel. That's a feeder. There's no loads on it other than at the end of it. A tap, which is a smaller conductor off of a feeder, or a bus bar, which is in a panel board construction. And so, and clearly, when we're talking about feeders, we don't mention the 120% rule. The 120% rule is only talked about when we're talking about the bus bar, and it doesn't apply to anything else, anything. So, a gentleman was asking me yesterday about a transformer, and some, inspector trying to apply the 120% rule to a transformer. Because you got the utility on one side of the transformer and you got the PV on the other side of the transformer, and so you upsize the transformer for the sum of the two outputs. And it's like the transformer can flow power in one direction at a time. It can either go this way or it can go this way. It can't go both directions at the same time. There's no way to add power in both directions. Now, if you have 2 feeds on the same end of a conductor, well, yeah, of course you can have more current flow on that conductor. They got to be both on the same end of the conductor in order to add their current. Opposite end doesn't work. The bigger one always wins. Whichever one is the bigger one, when we do an analysis, the conductor has to be sized for whichever overcurrent device is the larger overcurrent device. Okay, so I think we're pretty much out of time. We're going to go into a lot more detail about panel board connections and this whole thing that the 2014 code has done with breaking out feeders and taps and bus bars. And we'll do some examples and make that a lot clearer when we talk about these more advanced topics tomorrow afternoon from 1 to 4. You're welcome to join us or not. So thanks everybody for hanging out. Let's go have a beer and chat.